Geometry of supergravity.
Okay, firstly, I'd like to thank the organizers for the invitation. It's nice to present some work at this conference. So I'm going to talk about some work I've been doing with Andre Coimbra and Daniel Waldrum. A lot of it I did during my PhD at Imperial, and I've kept studying it while I've been at my postdoc in Hamburg. And I'm also going to talk a little bit about some work in progress at the end, which maybe might appear soon. We'll see what happens. So the main idea is that we want to use this wonderful mathematics of generalized geometry to completely reformulate all of the equations of supergravity. And it turns out that this is possible. And we're going to talk about ODD times R plus generalized geometry for type 2 supergravity, and EDD times R plus generalized geometry for 11-dimensional supergravity. And kind of the punchline is that we can write the bosonic sector of these theories in such a way that the equations look geometrical, exactly like GR, but in generalized geometry. We also find kind of miraculously that the supersymmetry in fermions comes out of this very nicely, even though we never put it in the construction. And we find that the symmetries are kind of unified, and we see the hidden symmetries appear. And it's just a kind of a nice structure. So the outline of the talk is, first I'll talk about some features of ordinary geometry and gravity in a way that will directly generalize to this other construction. Then I'll review some things about type 2 supergravity and its symmetries, and go on to geometrize it with O1010 times R plus generalized geometry. Then I'll talk about how you do the same thing for 11-dimensional supergravity with an exceptional generalized geometry, and make some further comments at the end. So we have a manifold M of dimension D with a tangent bundle Tm. And something we can think about is the frame bundle, which is the fiber bundle formed by whose fiber is the set of frames on the tangent bundle at each point. This is a principal bundle with structure group GLD. Something we'll be interested in is diffeomorphisms. An infinitesimal diffeomorphism is generated by a vector field on the manifold, and it acts by the Lie derivative. And the algebra of the Lie derivative is the Lie bracket. Now, the Lie derivative we're going to write in a particular way as being like the derivative along the vector in the manifold minus the adjoint action of the derivative of the vector. So we can think of this derivative of vector as being like a matrix in the Lie algebra of GLD. And if you convince yourself for a second, you can see that this is going to give you the formula that you know and love for the Lie derivative normally. We can also write connections on our tangent bundle, or in fact on any GLD tensor bundle. And given a connection, we can define its torsion using the Lie derivative. So we take the Lie derivative with the partial derivative replaced by the connection and subtract off the ordinary Lie derivative, and that gives us the torsion contracted on a vector. And this will be the definition which nicely generalizes. Now, naively from this definition, you might expect that the torsion can depend on all the components of the connection, but everyone knows that really it only depends on the antisymmetric part of the connection. And everything I've said so far hasn't mentioned a metric. But now I want to introduce a metric because gravity has the metric as its field. So we introduce a metric on the tangent bundle, which gives us an element of this coset at each point in the manifold. And instead of talking about the metric, we could equally talk about a principal subbundle of the frame bundle. So this is the subbundle of the frame bundle as given by the orthonormal frames at each point, and it has structure group, the Lorentz group, instead of GLD. So it's actually kind of easier to think about this instead of the metric in this talk. So having built that, we can ask, can we find connections which are compatible with the structure and which are also torsion-free? So everyone should be vaguely aware that in this case, the answer to this is yes. You can always find a torsion-free compatible connection. And it's the Levi-Civita connection, and it exists uniquely. And now, in the standard approach to gravity, you then go on to calculate some curvatures of this Levi-Civita connection. And these curvatures become the equations of motion for the theory, and the scalar curvature is the action. And all of these things are just defined by this principal subbundle. The metric, the Levi-Civita connection, and these curvatures you can determine all just from this. So this gives us kind of a plan for how to do the same thing in generalized geometry. So we define our generalized tangent bundle so that it matches the generators of the bosonic symmetries of the supergravity in the same way that vectors generate diffeomorphisms. We'll find that the structure group of this bundle is these groups in the cases of interest. We can then define the analogs of the Lie derivative, the connections, and the torsion on this generalized tangent space. And we then use the supergravity bosonic fields to define a principal subbundle or a reduced structure group on the generalized tangent space. We then look at the Levi-Civita connection and find that the resulting curvatures give us what we want. So that's basically the plan. So now some details. So in type 2 supergravity, we have the NS-NS sector bosons, which are a metric, a two-form, and a scalar. We'll also have some fermions in the game. And ignoring the RR sector completely for now, the Einstein equation is this, to zeroth order in fermions. And so at the end of the day, we'll discover that this can be thought of as a generalized curvature. So the symmetries here are, we still have the diffeomorphisms as before, but now we also have a gauge transformation of the B field, which is generated by a one form. So we're kind of thinking that we might be looking at something like vectors plus one forms as being the generalized tangent space. And you can sit down and calculate what the algebra of these transformations is, and it turns out to be the Courant bracket, which is kind of known in the mathematics literature. So it's looking hopeful. There's a slight technicality, though, which is that the B field is a potential, so in general it's only locally defined. So what we do is we split the manifold into little patches and put a two form on each patch such that they have a gauge transformation between the patches. And this implies that our gauge generator is also going to have some patching rule, which is given by this. So now we can define the generalized tangent space. You can view it as being an exact sequence like this, but we can think of this as just saying that a generalized vector is locally represented as a vector plus a one form. And between the patches of the manifold that we had before, the one form's just patches I had on the previous slide. And this means that a section of this generalized tangent bundle is going to be exactly the bosonic symmetry generator for the supergravity. And this is the same definition was originally written down by Hitchin and Galtieri. So the structure group of this is honestly GL10 semi-direct product with a shift. And this comes from the diffeomorphisms, and this comes from the gauge shifts. But this preserves a split signature norm on the generalized tangent space, which was basically just you contract the vector in the one form. And so we can view E as being an O1010 bundle because of the structure group preserves this norm. So we'll think of the frame bundle of E as actually being frames related by O1010 transformations. Okay. So now we want the generalizations of the Lie derivative, the connections, and the torsion. And we find that we can use pretty much the same formulae that we had before to do this. The Dorfman derivative is just given by the same formula as I had for the Lie derivative. Things to note are that this derivative means that you only differentiate along the vector direction in the manifold, because those are the only directions you can differentiate in. And this is a notation we'll use a lot, which means roughly you take the tensor product of the things either side of it, and then you do some projection onto some representation indicated here. So here we take something in E and something in E star, and we project it onto the adjoint of O1010. This formula gives you a well-defined object, it respects the patching symmetry of the generalized tangent space, because it turns out to have the right symmetries. And it can be roughly thought of as generating a diffeomorphism in a gauge transformation. It kind of acts by the Lie derivative by the vector and some appropriate shift action by the derivative of the one form. So we can also write generalized connections. And again, the definition is the same as for an ordinary connection, except now it's acting on O1010 tensors. And the torsion of these connections we can define again in the same way, except that now we use the Dorfman derivative instead of the Lie derivative. And we find that the torsion of one of these connections lives in the completely anti-symmetric part of the connection. So now we would be just about there if it wasn't for a slight subtlety to do with including the dilaton. If we proceeded with the tangent space that I had written down then, we would get everything right, but we wouldn't see the dilaton. So we want to see the dilaton in type 2 supergravity. So we need to define another bundle in addition to the one that we had before. And this we call E tilde. And it's basically defined in the same way, except instead of having vectors and one forms, you have vector densities and one form densities. And this means that the structure group gains an extra R plus factor. Now, we can write the Dorfman derivative in connections acting on this bundle E in the same way as before, roughly. But we are only going to take Dorfman derivatives and connections by a section of E, not a section of E tilde. Now, basically adding this R plus, the main impact of that on the theory is that the torsion gains an extra piece which looks like E, and that's going to accommodate the dilaton later. So now we want to define a reduced structure group on this using the supergravity bosons. It's well known that these supergravity fields parameterize this coset at each point in the manifold. And one way to see this is to use these fields to explicitly build a 091 times 091 family of frames, which you can do explicitly like this. The details are not so important. So we have one frame with an index A, and the other one has an index A bar, which transform under the two 091 groups. And so the span of these becomes C plus, and the span of these becomes C minus, and we've written E as an 091 times 091 structure. Okay, so this density appeared in the construction of this frame as this prefactor. And roughly all it's doing is making an isomorphism between E and E tilde. And using this, we can write the generalized metric of Hitchin and Galtieri in terms of the frame in just the same way you'd write the metric in terms of a Vielbein usually, except that we have more things involved. Okay. So now we want to see if we can do the analog of Levi-Civita connection in generalized geometry. And you can look at compatible connections, which basically means they just preserve the metric in this density. And we find that torsion-free compatible connection always exists, but there's no unique choice in this case. The condition of torsion-free and metric compatibility is not sufficient to fix the connection completely. But some components of it are fixed to be the supergravity field strengths H and d phi. So at this point, it's not looking so good, because this is different to how it works out in ordinary geometry. But what we'll find over the next few slides is that we can, in fact, still write a Ricci curvature for these generalized connections. And the magic is that if D is torsion-free, this does turn out to be uniquely defined by the structure. So it doesn't depend on which torsion-free compatible connection you choose to calculate it. So how do we do this? Well, the easiest way to do it turns out to be to think about spinors. So associated to each of C plus and C minus, i.e. basically the two SO91 groups that we have, we can write a spin bundle. And if we take spinors transforming in each of these things, we can construct 4 derivatives of it, which are just natural OD times OD, or O91 times O91 covariant projections of the generalized derivative acting on the spinor. And these things turn out to be uniquely defined. They don't depend on which torsion-free generalized connection you choose. And they look remarkably familiar when you evaluate them in some frame. And in fact, they're the supersymmetry variations of the theory. So you take the fermions in the theory and you promote them to transform under O91 times O91 in an appropriate way. And these unique operators then give you precisely the supersymmetry variations that you want. And also, very similar things give you the fermion equations of motion. So now we can use kind of physics, we can use supersymmetry to say, we know that taking the supersymmetry variation of the fermion equation of motion gives you a boson equation of motion. And so substituting these into these, you get some expression like this, which sure enough has a curvature tensor on the right-hand side of it. And because all of these things are constructed in a way that doesn't depend on which connection you choose, neither does this one. So we've kind of got there. We have this curvature tensor, which gives us the Einstein equation for the theory. Along the way, we've somehow written the SUSY variations and the fermion equations of motion very nicely in terms of these generalized derivatives. And we can also build a scalar curvature, which gives us the action if we want, and it's also the last equation of motion. So that was kind of the story for ODD times R plus generalized geometry.
Are you claiming that this simple Lagrangian gives you the full type 2 Lagrangian?
It gives me the full NSNS sector Lagrangian.
I see. Yeah. Do you have any?
So the fermion
to the Ramon?
Yes. Maybe I'll come to that in a minute. Okay, so let me just do 11-dimensional supergravity very quickly. So in 11 dimensions, we don't have the analog of the O1010. So we have to do a dimensional split, a la DeWitt and Nicolai and those authors. We choose the theory to we look at solutions of the theory basically with a warped metric ansatz like this. And we keep only fields associated to what would usually be the internal part of the compactification, which is the opposite of what you do usually. So what we basically land up with is, for this internal space, which we take to have dimension less than 7 for reasons that I'll come to, we have a field content like this, which is a metric, a 3-form, a 6-form, the warp factor, which is a scalar we can put in, and some fermions. The 6-form here is the 11-dimensional magnetic dual of the 3-form. Now these fields have some gauge transformation, which looks like this, and it's generated by a 2-form and a 5-form. So similarly to before, we guess that the generalized tangent space in this case is going to have a vector, a 2-form, and a 5-form. And it turns out we also need this bit in order to complete an E77 representation in 7 dimensions. And sure enough, this does become the GLD decomposition of the fundamental representation of EDD in D dimensions. So we have an EDD times R plus structure on this internal manifold. And then we can do exactly the same as before. Do everything the same. The Dorfman derivative, the connections, and the torsion are defined in exactly the same way as before. We can also use the bosonic fields to define what we call an HD structure. HD is the maximally compact subgroup of EDD here. So for example, for E77 is SU8. And we can promote the fermions to transform under this group HD. I'll say the gravitino transforms in a representation J, and the spin half-1 transforms in a representation S. And very similarly to before, we can write these nice projections of the generalized derivative acting on spinors, which give us the SUSY variations and fermion equations of motion. And again, the closure of the SUSY algebra gives you some generalized curvatures, which are the bosonic equations of motion. And this is a remarkably compact rewriting of these equations. These equations are truly horrible if you write them out in ordinary supergravity language. So I have a bit of time left. A slightly interesting little mathematical observation about this is that there's another EDD times R plus tensor, which is interesting here, which is this thing that we call the bundle N. And it's a subbundle of the symmetric product of two generalized tangent spaces. And its GLD decomposition looks like this. This is kind of like the gauge transformation of the gauge transformation. So this is like a gauge transformation of the 2 form, and this is a gauge transformation of the 5 form. And it has some interesting features. So for example, if we take partial derivatives, then usually in geometry you only have that anti-symmetrized partial derivatives vanish. Whereas here, you can see that partial derivatives projected onto this n star, a symmetric part of it, actually vanishes as well. Similarly, for the Dorfman derivative, we can look at the symmetrized Dorfman derivative. And this also can be written in terms of a projection onto this n bundle. You take the two vectors, project onto n, hit that with a partial derivative, and project back onto E, and that's the answer to this problem. And it also comes up in these curvatures. You can rewrite the curvatures that I had as a term that involves kind of like anti-symmetrized connections, and also a term that involves symmetrized connections projected to n. So this n is measuring kind of the failure of a lot of things to look like ordinary geometry here. And it roughly kind of says that it's expressing the fact that the generalized tangent space we're considering has such a much higher dimension than the manifold itself. So in double field theory-like approaches to this, they say that this is the section condition which recovers a physical space-time at the end. I don't want to talk so much about double field theory here, but I thought I should mention it there. So now, I kind of want to talk about something that I've been doing a bit more recently, which is very much work in progress for a couple of minutes, to do with when you can construct these generalized geometries, and can we do other algebras? And the answer seems to be definitely yes. So roughly, this is going to be very hand-wavy, and I've basically seen these patterns just by studying examples. I don't have a kind of general argument for why this should be true. But roughly, if we look at the GLD algebra, we can look at the Dinkin diagram and say, associated to each node, there's a fundamental representation. And I want to think of this one as being like the vector, the one at the other end as being like a 1 form, this one being like a 2 form, etc. So I then want to consider something like, what happens if I add a node to this Dinkin diagram at the node at the P form? Well, if I then say, maybe the node at this end is still the vector, I can look at the GLD decomposition, and I can look at the GLD decomposition of the adjoint, and it's kind of starting to look like generalized geometry with a P-form field. Similarly, I can look at this node here, which is 2 down from the P-form, and say maybe that's the N bundle. And again, the GLD decomposition kind of looks like it should be the N bundle. So this looks like generalized geometry with a metric, a P-form, and possibly some other stuff, and a scalar, forming the coset of basically the maximally split form of this Lie algebra divided by its maximal compact subgroup. So an example of this is if I do if I do ODD, but with the Dinkin diagram thought about the other way around. So usually in ODD, you put the extra node on this one here, which gives you the 2 form. However, here I want to put it at the other end and think of this node as being the generalized tangent space. And this is going to give me a D minus 2 form. So one example of this is to take D as 8 and look at spin 8, which is a subgroup of E8. And you find that, sure enough, you do the decompositions and it works out, I said on the previous slide, And it does indeed give you generalized geometry with a metric, a sixth form, and a scalar. And this is like a subsector of the fields for if I'd reduced 11-dimensional supergravity to 3 dimensions on an 8-dimensional space. And this one, actually, you can do in other dimensions. It roughly corresponds to keeping the even levels of EDD under GLD. So in E77, this is an SL8 subalgebra, and in E66, it's SL6 times SL2. If I wanted to go to 9 dimensions, it would give me back E99 again. And in actual fact, this algebra side of things, I can do for considerably more complicated things as well, subject to some caveats. So one thing you could look at would be this. This is kind of like associated to 6-dimensional n equal 1 supergravity compactified to 3 dimensions. If I say that this node is the generalized tangent space, I can do the decompositions, and it gives me the right kind of field content that I want. But like many of these things, this one does not give me a generalized geometry. And the only, well, not the only reason, but one of the main reasons you can see this is from the appearance of these mixed symmetry tensors. Here, I have a mixed symmetry tensor in the tangent space, and I have a mixed symmetry tensor in the adjoint. And basically, when I form the Dorfman derivative for this thing, I'm going to need to somehow form one of these from a partial derivative of one of these. And you can see fairly quickly that that's never going to be the diffeomorphism covariant. So when these mixed symmetry tensors appear in these algebraic decompositions, the Dorfman derivative fails to be covariant, and you can't really do much. So, for example, this also happens in E88 for basically the same reason. This is thought of as being the dual graviton in 6 dimensions, and you get the analog in 11 dimensions for E88. However, this is all just present in the pure gravity case. So if I could solve this in the pure gravity case, then via this kind of construction, I'd be able to write the analogous things for generalized geometries for virtually anything. Now, I have 2 minutes. So I'll skip through this very quickly, but I was going to tell you about how when you do supersymmetric compactifications of these things, the levels of supersymmetry that you get in the effective theory correspond very nicely to G structures on the generalized tangent space, and that you can vaguely see the embedding tensor coming out of this. And there's also a very nice result that I can say here, which is if I want a supersymmetric background, then the Killing spinor equations become equivalent to the existence of a torsion-free compatible connection which preserves the Killing spinors. And so in generalized geometry, a supersymmetric background, even including all of the fluxes, becomes basically just the analog of special holonomy for this generalized derivative. This is an idea that's been around for a while, and this really makes it work. So just quickly, I'll mention some other things you could wonder. So I've been said a few times that dual gravity is a problem here. And it is a problem, and I don't know how to deal with this. But if I did, then it would open up really very large possibilities.
What do you mean?
So this charge here is argued in the literature to be like a magnetic joule of gravity, somehow. Nobody, I think, really has a good idea of how to deal with this. But it's clearly a problem because you can't write the gauge transformations associated to this object and things in a way that respects diffeomorphism symmetry. So it's clearly very problematic. That's all I mean. There's also questions about non-geometric backgrounds. If I could have similar bundles to this which really genuinely were ODD or EDD structures, maybe that might be related to non-geometric backgrounds in string theory. I could wonder, can I write this with super algebras in it somehow? I could wonder about higher order corrections. Recently there was this paper by Holm, Siegel, and Zwiebach that think about this in a double formalism, and that looks quite interesting. And then in maths, there's this n-bundle structure, which I don't know whether there could be some theory behind that. There's gerb-like structures appearing in these exceptional geometries, which I don't know if they've been looked at before. And there's this generalized special holonomy question. There's lots of theorems about special holonomy manifolds. Can we say something similar for generalized special holonomy? I don't know. But thanks for your attention. I'll stop there.
Maybe we can have 1 or 2 questions while the next one gets set up, so we can get into it.
Cases where you have the 11D supergravity capital to 10D super angle. I mean, is there going to be some nice structure you can say about backgrounds and such?
Possibly. I mean, so in this 6D example I had, there are similar things which incorporate vector multiplets and tensor multiplets in this. So I can do things like that. The situation you refer to, I'm not so sure about, but maybe.
Let's thank Charles again.